Hello, welcome to Fundamentals of Acoustics. Today is the third day of the 11th week of this course, and today we will continue our discussion on sensitivity of microphones. Yesterday we had stated that while defining microphone sensitivity, there are two reference standards. One standard is for a mic which generates 1 volts for each Pascal sensed by it, and the other standard corresponds to 1 volt for each microbar. So, what we plan to do today is do a small numerical example for the second standard, and using our method we will compute the voltage generated by a microphone for such a device. So, we will do an example, and let us say that sensitivity of the microphone is still minus 26 decibels, but instead of 1 volt per Pascal, our reference is 1 volt per microbar, and 1 microbar is equal to 0.1 Pascals. Okay. So, question, this is the question we have to answer. How many volts are produced when dB SPL equals 20 decibels. So, when there is sound pressure level of 20, what is the value of volts generated by this mic? So, first compute, what we will do is we will compute how many volts are produced for each Pascal, and then we will accordingly do the math. So, Ls equals minus 26 decibels, and that equals 20 log of 10 Y by Y ref. So, that gives me Y equals 10 to the power of minus 26 by 20 is equal to 0.0501. Now, what is the unit here? Volts per microbar, which means that if the microphone is subjected to 0.1 Pascals, it will generate 0.05 volts. So, alternatively I can write it is as 0.501 volts per Pascal. Okay. So, now dB for SPL, this equals, we are saying that it is 20 decibels, that equals 20 log 10 P RMS divided by P ref. So, P RMS equals 20 into 10 to the power of minus 5 times 10 to the power of 20 divided by 20. So, that works out to be 20 into 10 to the power of minus 4 Pascals, or it is 2 into 10 to the power of minus 3 Pascals. So, then volts generated this is volts generated is what? Is equal to 0.501 times 2 into 10 to the power of minus 3. So, that comes to 10 to the power of minus 3 volts. So, So, our reference pressure is 20 micropascals or 2 into 10 to the power of minus 6. So, that becomes 20 into 10 to the power of minus 5 or 2 into 10 to the power of minus 4. So, if I multiply this number, so this should be 4. So, if I multiply this number, it is 10 to the power of minus 4 volts roughly, because 2 times 0.501 is about 1. So, that is 0.1 millivolt. Okay. So, it is important to understand the the significance of this reference number, because based on this reference number, this value y changes. The next thing I plan to do today is discuss microphones. What we will do is so earlier we had classified our microphones from the standpoint of working, but perhaps an important way to classify microphones is based on application. Classification of mics by application. Now, in general, there are 3 broad categories of mics if we classify them by application. The first type of microphone is known as diffuse field microphone. The second type of microphone is called free field microphone. And the third type of microphone is called pressure field microphone. Pressure. So, these are 3 classifications of microphones based on application, and we should understand what these terms mean. So, what is a diffuse field? A diffuse field would be, suppose you have a room, suppose there is a room, and typically rooms are not just rectangular volumes, they may have some slanted surfaces. So, if I have a sound source here, it comes to this edge, it gets reflected again, it gets reflected. So, you may have reflections coming from all the directions. So, if in such a room where reflections are coming from all the directions, we want to measure sound pressure level, we need a microphone which can sense sound waves coming from all the directions. So, we need a microphone. So, let us say this is our microphone and it is sensitive to sound coming from all the directions. These types of microphones, so here the sound pressure field is diffuse, it is not in one particular direction, it is all over the place. Okay? At every point sound is coming from all the directions. These types of microphones are also called random incidence microphones. Random incidence microphones, because the noise is coming, the incident angle of the noise which is striking the microphone is at all sorts of angles. So, it is randomly oriented. Okay. So, this is one. Second thing, they are also known as reverberation field microphones. So, these diffuse field microphones are also known as random incidence microphones or reverberation field microphones. Why is it known as reverberation field microphones? Because when sound comes, it hits a reflecting surface, comes back, so it has a lot of reverberations. So, the sound in the room or closed space has a lot of reverberations. So, a microphone which is sensitive to sound coming from all directions will measure also reverberations accurately. Okay. So, this is one category of microphones, which is diffuse field microphone. The second category of microphone is known as free field microphone. Now, what is free field? So, imagine that you have in air there is a bird which is chirping, and maybe 50 meters away from there in the air you want to see how much sound is coming from that bird. So, in such a case your sound field is typically like this. Sound waves are traveling in a particular direction, So, there is a bird or there is a speaker and the sound is going like that, okay. And your microphone should be of a nature that it is sensitive to a particular direction, which is the direction of the sound, the direction from where the sound is coming. So, these are free field microphones. In free field microphones, so what is there? When do we have a free field? We have a diffuse field when we have lot of reflections. So, free field occurs when no reflections occur, and this typically happens when there are no hard surfaces or reflecting surfaces. So, typically it can happen when you are way up in the air. So, that is one area, or if you are on the ground and you are sufficiently above the ground, so that sound does not get chance to come hit the ground and again approach you. So, whatever sound you are receiving your microphone, it is coming directly from the source. Okay. So, that is also a free field situation, and we can create free field conditions in rooms by using anechoic chambers. So, in anechoic rooms, so anechoic means a room where there are no echoes. So, now if I have a sound source here and I have a microphone here, all the sound which it will sense only the free field sound, because the room is lined with materials and geometries, so that there are no reflections coming back to the microphone. So, this is the second category of microphones, free field microphones. So, we have to be aware whether we are making free field measurements or diffuse field measurements. The third category is pressure field microphones. Now, what is a pressure field? So, imagine a box, or let us say a tube, and this tube is being excited by some piston. So, sound is travelling here, right, and sound is also getting reflected here, but across this cross section the sound pressure level does not change, So, and if the length of this tube, so let us say this length, if length of this tube is very small compared to 1/6 of the wavelength, then sound is not only having same value across the cross section, but it will also have same value at different points in the tube. We can show that mathematically, because the pressure will have a component. So, what is pressure? P x t is equal to what? P plus E j omega x over c negative plus P minus E minus j omega x over c. If x is very small, which means the length of the tube is very small, then this term goes away, then the overall pressure in the tube will be, it will be approximately equal to P plus P minus, right, if x, the maximum value of x is very small, and that will happen only when length of the tube is small. Okay. So, in such a case the pressure is uniform in the whole tube, So, now I want a microphone. So, how do I measure pressure in such a tube? I insert it from one end, and the microphone should be sensitive to pressure in a uniform field. These type of microphones are called pressure field microphones. They are called pressure field microphones. Normally, we can use these diffuse field microphones also in pressure field microphones, because these microphones are, they can sense sound coming from all sorts of directions. So, if I use this in a pressure field situation, then it will work here. Now, these pressure fields microphones, where do we use? We typically use them in small closed volumes. Now, this volume could be a tube or a sphere or whatever. So, volumes and cavities. And what is the meaning of small? That the maximum dimension D max of the volume should be very small compared to 1/6 of the wavelength. Okay. So, three types of microphones: diffuse microphones, free field microphones, and pressure field microphones. And based on the measurement we want to do, we have to select our microphone carefully, other we may get totally wrong results. So, whenever in your field you want to do some measurement, first understand whether your sound field is diffuse, which means does it have a lot of reflections, or is it free field, or is it a pressure field, and accordingly you choose the nature of microphones. Last thing about microphones is about their size. Size of microphones. Now, microphones comes in all sizes. So, let us say this is a microphone and this is the diameter. Lot of times this diameter is either half inch or 1/4 inch, or in very few cases we may get very thin microphones, 1/8 inch. So, half inch is about 12-13 millimeters, 1/4 inch is about 6 to 7 millimeters, and 1/8 inch is about 3 millimeters wide. Now, the size of microphone should be carefully chosen such that D should be significantly smaller than lambda over 2 pi. What is lambda? Here lambda is the wavelength of highest frequency of interest. This is important to understand. What does that mean? Example, suppose I am interested in measuring sound and I think that the frequencies of this sound may be from 100 hertz to 5000 hertz. Then for this range of frequencies, lambda max will be what? C over 100. So, C is 345 meters per second. So, that comes to 3.45 meters. And the minimum wavelength corresponds to 5000 hertz. So, C min equals 345 divided by 5000, and that comes to 0.069 meters or 6.9 centimeters. So, lambda over 2 pi minimum value is equal to 6.9 divided by 6, 6.9 divided by 6. So, this is equal to 1.1 centimeters. 1.1 centimeters. So, for this application, if I use a microphone, let us say half inch. So, half inch means what? 13 millimeters, 1/4 inch means 6.5 millimeters, and 1/8 inch means 3.3 millimeters roughly. Huh? So, if I use this microphone, what will happen? Say suppose we are talking about free field, then waves will be travelling like this, and when I introduce a microphone which is fat, then the nature of waves will change. So, the sound field will get disturbed if I use a thicker microphone. If I use this microphone, maybe it will work. If I use this microphone, the sound field will get disturbed the least amount. So, we have to make sure that the size of the microphone does not disturb the overall sound field, and that will happen when this parameter lambda over 2 pi, its minimum value, is less than or it exceeds the size of the microphone. So, that is important to understand. So, that concludes the discussion for today, and tomorrow we will start discussing a new concept known as weighting. So, we will discuss the concept of weighting, and with that we close our discussion, and we will meet once again tomorrow. Thank you. Bye.